Okay, so now that we have created our mathematical model, that's the first thing that we are asked to do. And so the second thing we need to do is, of course, build the spreadsheet and actually solve the problem. Now, in order to save myself some time for the video and also to shorten the video a little bit, I have taken the luxury of making a template that already has the input variables and some other things in it. So I'm just going to copy and paste that in here. So I'll talk about it briefly, but I thought this would be a lot faster than me trying to explain and type in all the data and things like that. So, and some of this is already contained over here in our mathematical model, our parameter values, our trim loss, our demand. In fact, all of that is contained over here. So in addition to that, when we make our decision, we're going to be deciding how many patterns to cut. So as per usual, that's highlighted in red with the red border. Then that will correspond to produce rolls of 12, 15, and 30 feet. We'll need to compare that to our rolls required, and that will allow us to calculate our trim waste. So, as per normal, let's just start with the patterns cut and put something in there that gets us something to work with. I'm just going to put in 10. It doesn't matter what you put, and in fact, you can put in nothing, and it still works. Okay, so then we must ask ourselves, how many 12-foot rolls are produced? Well, we produce 0 from pattern 1, so we don't need to worry about how many patterns of 1 we make. We don't get any from pattern 2, so again, we can skip it. But we get 8 times 10, 80 from pattern 3, 2 times 10, 20 from pattern 4, and 7 times 10, 70 from pattern 5. So that should be about 170 rolls. And what I just described is, of course, a sum product function. So I'll go ahead and type that in. And like we predicted, it is 170 feet. Okay, now the careful observer will notice that we missed an absolute cell reference here before we can drag it over. But just for the sake of the demonstration, I'm going to go ahead and drag it just so we see, darn, this one was supposed to hold in place. Now, depending on the section that you attend, you may or may not have heard my metaphor about duct tape and WD-40. But in this case, the red bordered cells moved when they shouldn't have. And when something is moving that shouldn't move, that is when you put duct tape on it, or a dollar sign. So note the word dollar and duct both start with D, and so we remember that things that do move and shouldn't be moving need dollar signs. So we can go and we can type this in if we like, or you can use the F4 key. But what's important is that we get these absolute cell references in there, and then when we fill it across, perfect. Now we're sum producting the correct ranges. Okay, now our rolls required are simply our demand. So we make a relative reference to sort of point, if you will, with the air quotes, to point towards the demand and the demand for each section, until really it's as simple as that. So of course, we need to be producing more, not less, more than we are required to produce. So what that leaves is our trim waste, which is simply the sum product of our trim loss and our decision variables. So with our current situation, we only have 260 feet of trim loss. However, we are not even close to meeting our demand. So we are going to need to find a better solution in order to actually have a feasible solution. So let's go to Solver, and we are going to need to choose our objective. So what's our objective? Well, we are trying to minimize trim waste. So this is set to maximum. I better make it minimum. Minimize trim waste. We change our variable cells, which are always our decision variables. So on my templates, those are the ones that are in red, which will help you on your final exam, by the way. So we change our red bordered decision variables, and we have to enforce our constraint. But we only have one, and that is that our rolls produced must be greater than or equal to our rolls required. Well, I shouldn't say there's only one. There is one more that's very important, and that is our integer decision variables. So we must produce whole patterns. You can't produce a third of a pattern. So B12 through B16 must be integers. Okay, and if you always need to remember to check, see we have nonlinear. That's not good. We want to change this to simplex. So just a good reminder. Whoops, I didn't mean to uncheck that. All right, so our objective, B23, minimize, decision variables are integer, and that greater than that. Okay, looks good. Let's give it a solve. All right, so what we found is not producing any of the first three patterns, producing 1,675 rolls of pattern 4 and 332 rolls of pattern 5. This gives us a total trim waste of 2,007 feet, which is the fewest that we can do while still producing enough of all of our rolls.